So the chapter that we're going to talk about is electromagnetic induction. And in this topic, what we have to do is what Faradays did. Faraday was the name of the person who was actually trying to find out, who actually accidentally identified that moving a magnet close to a coil or close to a conductor, just a moment. So moving a magnet close to a coil actually produces an induced EMF. Now we know from the chapter of EMF that EMF is basically voltage, and if we have voltage, that means that we can derive the electron through the circuit. So EMF is voltage, and having voltage means that we can drive a charge through a circuit. And flow of electrons is basically the current itself, right? And let's try to see what he was trying to do. So this is the setup that he had with him. So let's try to label what every part is. So this is our galvanometer, and this is our permanent magnet that we have. This is just a permanent magnet. So what he found out was, and this is a coil of wire, and we call a coil of wire as a solenoid as well. This is just a name, different name for that. Okay, so permanent magnet, what we were trying to do is, he was moving the magnet in and out of the system. What he saw was that as long as the magnet is moving in the presence of a conductor, we made the coil so that we can amplify the effect. We could see it more clearly, otherwise one coil could have done the job as well. But in that circumstance, in that case, the magnetic field or the magnet has to be very strong in order for us to see the effect. So just to exaggerate the situation, to understand it better, what we've done is we have introduced more number of coils. I'm going to use a very strong magnet for this process to be actually visible. Okay, so what he identified was, in plain and simple words, as long as the magnet is moving, there is an induced EMF. Induced EMF. You see, why do we call this induced EMF? Because there is no physical connection between the coil and the magnet. They're not physically connected. They are just present in each other's vicinity or in each other's presence, right? Or the neighborhood of each other. So under these circumstances, what he identified is that as long as the magnet is moving, there will be an induced EMF. Now, let's get more technical about this. What he was looking at was, what he was trying to say was that since the magnetic field exists like this around the magnet, right? So as long as this magnetic field is cutting the coil, the words that you have to write down in the question or in the answer is that magnetic field is cutting the coil. And of course, if this is just a single wire, then we would have to write down conductor. And this cutting of magnetic field, or this exposure of changing magnetic field, leads to induced EMF. So cutting of magnetic field, or what you could have written down, is that changing magnetic field is producing an induced EMF. So all of this leads to the idea of induced EMF. Now, we get EMF because one of them is moving, and please be mindful, it's not only fixed for the magnet. Even if the magnet was stationary and the coil was moving, it would still produce the same effect, because at the end of the day, the thing that is required is the cutting of the magnetic field. Either magnet moves and does that job, or either the magnet is stationary and the coil starts moving in the presence of a magnet and it will do the same job. So as long as the magnetic field lines of a magnet are being cut by a conductor, there will be an induced EMF. Now, for the induced EMF, what we say is that there is no element at this point. For example, And when we measured it with simple voltmeter, because voltmeter is what measures voltage, so when we measured it with a simple voltmeter, we found voltage. We found that the needle is actually moving in this direction, representing a voltage, right? Now, this is induced EMF. If you want this to cause induced current, then you'll have to connect all of this setup with a resistor so that current may flow. So the same, for example, coil and magnet setup, and if you connect a bulb with it, a load or a resistor, this induced EMF will now cause induced current. Because if we have voltage, as we've just done before, if we have voltage, it can cause or it can help us derive a charge through the circuit. So if we have EMF, if we have induced EMF, then we can complete the circuit and cause an induced current, which is of course going to light up the bulb as long as the magnet is moving, right? Okay, so the purpose of the galvanometer is to detect the current or very small amount of current that is usually in the range of microamperes, right? Now, there's another idea behind this. What he identified was that whenever he changes the direction of the magnet, the direction of the induced EMF also changes. So for the sake of example, let's say, and again, this is all just hypothetical. The examples are hypothetical, but the directions have to be found properly. Do you remember the right-hand grip rule? Right? So in that right-hand grip rule, we figured out that we can figure out the direction of the magnetic field around the conductor if we know, we can figure out the direction of north and south pole if we know the direction of the current. So for example, if this is the direction of the current, then I would have to use my right hand grip rule in this way, that this would be my thumb and my fingers would be curling in this way, trying to grip the conductor as we have discussed previously. And of course, be advised, we are using the right hand, not the left one. So my thumb is pointing towards the north pole. So this side would become the north pole and this side would become the south pole. Again, if the direction of the current were to be reversed, then what I would find is, for example, that the current is now flowing in the opposite direction. In this case, I'll have to use the right hand grip rule and try to grip the conductor from behind with the curl of my fingers, representing the direction of my current. And if I do so, my thumb opens up in this direction. So in this case, the north pole would be in this direction and the south pole would be in this direction. So I'm color coding this so that we understand what it is. Okay, this is how we used to find it, right? Now, we are not going to get into this detail. We are just going to understand that as long as the magnet is moving, it produces an EMF, and of course, if the load is connected, then it will be called induced current. So over here, what the problem faced by Faraday, or the answer he was still looking for, was not that the magnet moving causes, or the changing magnetic field, or the cutting of magnetic field causes an induced EMF. The answer that he was looking for is the direction of the current. You see, what he observed was that if the north pole is brought closer to it, right, for the sake of example, and again, this will be found by using the right hand grip rule, which we're not getting into right now. What he observed was that when he brought the magnet closer to the coil, the current that flowed in the circuit would look something like this, and the needle would be pointing towards the right side, depicting that the current is actually moving in this direction, or you can say in this direction. And when he took the magnet away from this apparatus, for example, in the backwards direction, again, the condition is satisfied, the magnet is moving, the magnetic field would be cut by the coil. So an induced EMF or induced current should be there. What he found was that the current now started moving in the opposite direction through the galvanometer in this way. And how would he observe this? Is that the needle would start pointing in this direction, depicting that the direction of the current has changed. He could not find the answer to this question. So later, another scientist by the name of Lenz actually came up with a reason for that. That why is this happening? But up to this point, do we understand that? So this is what Faraday could not figure out, why the needle is pointing towards both directions, and of course, depending upon the direction of the magnet. And for the sake of example, we were saying that if I bring magnet closer to the coil, it causes a deflection on the left side, or left deflection. And if it is taken away from it, it causes a right side deflection, or right deflection. Alright? Okay, so moving ahead from this point, we now move towards Lenz's law. And we can see that over here, when the magnet was being brought closer to the coil starts pointing towards the left side. And when the magnet becomes stationary, it stops moving. Now, since there is no changing magnetic field, although the magnet is placed very close to the coil, there is no change in magnetic field, so there will be no induced EMF, and hence the galvanometer will show us a 0 reading. So that's why we started the class with this premise that as long as the magnet is moving, or as long as the magnetic field is being cut, or as long as the magnetic field lines are crossing through the conductor or are cutting the conductor, there will be an induced EMF. Similarly, when we go to the lower side, when the magnet is being brought or is being taken away from the coil, it causes such a current in the circuit that now the current is actually pointing towards the right side. So this change in direction of current based on the change in direction of the magnet was he was unable to explain this. You see over here we have approximately 4 different configurations. You see, first he tries to bring in a south pole and then takes away the south pole and sees the behavior. Then he does the same experiment with the north pole being brought closer to it and then taken away from it. It didn't change except, of course, the value of the current or the magnitude of the current in terms of its direction. It only affected that. But then again, it couldn't solve the problem. Why is it changing the direction of the current if the direction of the conductor is being changed? Sorry, the direction of the magnet movement is being changed. So Lenz's came up with that reason, but for the sake of understanding, let's try to read the definition of Faraday's law so that we can understand it fully and we can move ahead. The other thing the Faradays actually came up with was that if I change the speed of the magnet, if the speed is higher, then the magnitude of induced EMF is also higher. So this is why he says that the rate of change of magnetic field lines. This basically means the speed of the movement of the magnet. So if there is higher cutting, there is going to be more magnitude of EMF even for the same amount of motion, or even for the same amount of magnet and the coil. If you do it quickly, there will be higher induced EMF. If you do it slowly, there will be a smaller EMF, right? But then again, there will be EMF. So the changing of magnetic field leading to EMF and increasing the speed or changing the speed of the magnet leading to a changing induced EMF, these are the 2 things identified by Faraday. Okay, but then again, it still was not able to explain the direction change by the magnet. So now we move towards Lenz's law over here. What Lenz was trying to identify was, he was trying to answer the question put by Faraday, that why the direction of the current is changing because of the change of the magnet. You see, let's exaggerate the situation deliberately and stand on the opposite end. What would have happened if that was not the case? Now let's see what Lenz actually saw. You see, Lenz actually saw this behavior in this manner, that if you try to bring a north pole closer to it, this action will of course cause a flow of current in the circuit, and we've established by Faraday law. But this current will be in such a direction that if I apply right hand grip rule on this, it would have indicated that there is going to be a north pole produced by this coil on this side. So north and north are actually going to repel each other. So this actually opposed or try to oppose this in the first place. Secondly, if they try to take this conductor or this magnet away from it, for the sake of example, right? So when they try to take it away, for example, the same North Pole that was brought closer to it, this motion or this way actually caused such a flow of current in the coil that when I applied right hand grip rule, I found that this is going to be the South Pole, or the coil's end closer to the magnet is behaving like a South Pole, and this is going to attract or is going to try to attract the North Pole or prevent it from moving away. This sense of opposition was identified by Lenz or by Lenz, which eventually came to be known as Lenz's law. Now let's try to see it in the context what the definition is trying to tell us. Okay, so the definition says that the direction of the induced EMF, again we are interested in the direction of the current in the coil, and hence the induced current, of course the current flowed by or due to the induced EMF, is always such that its magnetic effect, its own magnetic effect, again I explained that the magnetic effect of the coil itself, which has the current in the first place because of the magnet. If the magnet wasn't there, there would be no current in the coil, right? So if the magnet is there, its motion produced a current in the coil, and now the current in the coil is such that it is trying to oppose the motion of the magnet that is trying to produce it in the first place. Or you can say, simply put, it is opposing its own maker. You see, if the magnet was not here, there would be no current. Simple as that, right? Now the magnet is moving either close to it or rather away from it, and this cutting of magnetic field is causing an induced EMF in the coil. But the current in the coil is such that whatever the external magnet is trying to do, the coil produces such a magnetic pole that it opposes the motion of that magnet. So we end up with four possibilities. The first possibility is that if we try to bring in a North Pole close to it, this will become a North Pole, trying to oppose it. If we try to take the North Pole away from it, this will become a South Pole, trying to stop it again. You see, when it wants to come close, it would prevent it from coming close. When it wants to go away, it would try to prevent it from going away. So when I say that it is trying to do that, it means that it's not successful in doing so. It's not possible, or it's not going to be this way, that the coil eventually stops the motion of the magnet. It defeats the whole purpose. You will feel a certain sense of opposition as it is happening, as it is going on, right? And on the other hand, if we have a coil again with a South Pole, again another coil with a South Pole, let's bring South Pole close to it, this will produce a South Pole. Again, if the magnet wants to come close to it, the coil produces such a pole that it will try to prevent it from coming even closer. If the magnet is trying to go away, it would try, or the coil would produce such a pole due to the flow of current in such a direction that it would now try to prevent it from going away. So whatever the maker or its own producer, that is the magnet on the outside, is trying to do, the current of the coil is always trying to oppose it. Do we understand the meaning now? This idea is not, you can say, is not peculiar. It's not very out of, you can say, out of the ordinary. You see, later, let's try to create a situation in which we can go to such an extreme that it is unbearable, or it is so exaggerated that it is impossible that it would ever exist. If we observe that situation, then it will help us to understand why we find this situation to be like that. Okay, so for the sake of example, I'm opening up the coil in multiple loops that they may look like this to us. We are bringing a North Pole closer to it. We've exaggerated the situation by opening up the loop and visualizing each loop separately. So what we have observed is that it should produce a north pole so that it can oppose the magnet from coming even closer. Let's say if this didn't happen, let's say that if north pole was not the answer and it actually created a south pole, for the sake of example. So our motion of the magnet induced such a current in the coil that caused a south pole closer to the magnet. Now we know that north and south are attracted to each other. So what it effectively means that I just had to push the magnet once and it would automatically be attracted to the coil. Once it crosses this coil, it encounters the next one. And again, movement of the magnet produces the south pole on the coil, of course, which will produce another attractive force. And the coil or the magnet actually ends up at this location. But since it is already moving, it has its own inertia, so it continues to move and experiences a changing magnetic field for this whole coil, or provides a changing magnetic field for the whole coil, again causing an induced current, producing a south pole at this point. So that would actually be an infinite energy system. You see, what I could have done is connected a full loop and introduced a tiny magnet in this loop and forever let it to happen, or forever let it move through the coil, and I could just connect a bulb through it, and this would be an infinite energy system. This is impossible according to the idea of universal law of conservation of energy. We cannot get more than what we put into the machine. So this idea that actually Lenz came up with was in tune, or was in line with the universal law of conservation of energy. Let's try to discuss this one more time. This is the extreme scenario that if it didn't happen this way, then what would have been the possibility? But what happens in reality is that we're not getting the south pole, we're getting the north pole if it is trying to come closer to us. This is the north pole, this is the north pole, this is the north pole. So the magnet, whatever is trying to move the magnet, or whatever factor is trying to move the magnet, will always face a sense of opposition from the coil. So for this action to be constantly in the working condition, we would always have to cause or provide some energy or some effort or some pushing force for the magnet to be always be in a pushing condition. You see, if I stop pushing the magnet at any stage, the north pole would eventually dominate the situation and try to stop or eventually stop the magnet from moving altogether. And if the system is producing electricity or current, then it would stop doing that altogether. This is exactly why for an AC generator that we're using to produce electrical current for house, for industries, and for, let's say, the whole world that we're powering right now, if the AC generator has more load onto it, for example, if you connect more houses, you connect more industries, connect more load onto it, the effort required to rotate this generator also increases, because there is a magnet inside the generator that is turning in the presence of a coil. That coil is connected to everyone. So when the magnet rotates, the coil experiences a change in magnetic field, produces an EMF. That EMF is utilized as induced current for all the appliances working in our country, or in our whoever is the end user of that. So if you keep on loading the generator with more and more load, there will be a higher current in the coil. A higher current in the coil would make the magnetic field of the coil more stronger, so providing a stronger opposition to the permanent magnet that is trying to rotate in the presence of the coil. That is why if an AC generator is rotating, you put in more load onto it, it would get more difficult to rotate it. Because as soon as the magnet starts rotating, the current produced in the external coils that we have on the generator, we will look at the construction of this as well. The external coils that we have on the generator do experience an induced EMF, but once that current starts flowing, it has its own magnetic field, which starts opposing the magnetic field of the permanent magnet that's rotating in the first place. So when it starts opposing, rotating the generator becomes more difficult. So we'll have to put in more power. If you have connected it with an engine or a turbine, or let's say or with a dam, so you'll have to provide more water flow, more petrol, a powerful engine, more nuclear power, or more steam production from the turbine, for the turbine of course, to eventually rotate it even faster so that it can keep up with the loading effect that we have provided. Do we understand the bigger picture for this?